Welcome to the first of several training videos presented in partnership with Precision Optical Technologies. In this series, Jarek Markeloff and I are going to introduce you to what is a small form pluggable transceiver, why we need them, the evolution of optical transceivers, what's inside them, and some considerations when choosing the right optics for your application. Make sure you check out all that Precision has to offer your network by following the link in the comments section below.
So, introduction to transceivers. What is a transceiver? So, transceiver is actually an amalgamation of transmitter and receiver. So, typically what you will see is a pretty standard SFP will have a transmit and a receive port to it. There are some applications in the industry where we'll see, a transceiver that acts as just a transmitter or a transceiver that acts as just a receiver. But by and large, when you say transceiver, we're talking about a device that's able to transmit and receive optical data. So what are the basic components? Metal casing. This determines the form factor and size of the transceiver. I added heat sink to this component because sometimes the metal casing itself can be designed to act as a heat sink in itself. Other times you'll just have some, we refer to as just a heat paste inside of the transceiver. You don't see it. It almost has the consistency of like a toothpaste in a way, but won't see it. Electrical connector. So this is the board to the backplane electrical connector. Basically, this is what's going to touch the host device. And this is where you begin to see the conversion of an electrical computer signal into an optical signal. So the switch or router is finally, this is where it's transferring the data. Microcontroller, this is what controls the EEPROM for compatibility and programming. So EEPROM, I don't have it explained here, but EEPROM stands for electronically erasable programmable memory. And for a transceiver, this is like your driver's license. It's the transceiver's way to identify itself to the switch or router. And it does so via an I2C serial bus. And at a high level, think of it as an electronic handshake. The host sends some data to the transceiver and it identifies itself. The transceiver sends the data back to the host and it identifies itself as well. This is the point of where compatibility between the host and transceiver is determined. If the host sees an EEPROM it doesn't like, it won't turn the SFP on. Or it'll look for specific data within the EEPROM and says, yep, you hit this check mark, you hit that check mark. I'm going to start feeding you some power. We're going to turn you on.
Got
it. So next is the digital signal processor. This is to help support the processing of NRZ, PAM4 coherent. Basically, NRZ stands for non-return to zero. That's your on-off keying. Think of, the transceiver, the optical signal acting just like Morse code. There's the receiver see light, does it not see light? And from there, it can take one bit of information. PAM4 is looking at kind of the gray areas between no light and yes light. And basically, the receiver is able to take one optical signal and encode 2 bits of data. And then lastly, coherent. This is a very big buzzword in the industry right now.
Yes, it is.
And that one is a little bit more challenging to explain without some sort of diagram. I do have that later in the presentation that I can use. But
okay, well, we'll shelf the coherent optics for the moment.
Yeah, we'll shelf. Yeah. Next, you got the laser driver and the transimpedance amplifier. So the laser driver sits on the TX side. The transimpedance amplifier is the RX side. Then last, you've got your TOSA and your ROSA. So the TOSA is your transmit optical subassembly. Your ROSA is your receive optical subassembly, and can be comprised of a PIN or APD receiver with a transimpedance amplifier to convert current to voltage. Um, Something that we do get asked quite a lot is, how does optics work from the standpoint of, like, you shoot it at something, how does that receiver react? Well, so one of the almost kind of mind-blowing, most fascinating things about this is we will shoot a light, and this ROSA will be able to measure the electrical current that that light gives off. And that is so small and minuscule, but it's measurable. So like all light gives off a very faint amount of like electrical activity. And so through that, that's how we're able to, it's one thing to be able to convert electrical into optical, but it's the concept of reverting it back that to me is just really fascinating.
Well, both sides of it actually are really fascinating to think about taking an electrical signal and turning it into an optical, and then the reverse. The transceivers, and an amalgamated word is not uncommon, right? Because we also have modems, which are modulators and demodulators, is pretty similar. But what is amazing to me is there's a lot of stuff in that little box. Considering particularly the heat sink, right? There's a lot of activity happening inside of there, a lot of communication back and forth, the generation and reception of optical and electrical signals, all happening inside that tiny little metal case. So heat is a big deal, right? Especially as you start to send more and more data from that transceiver. So I don't want to blast past that one, because temperature management is pretty important. And one of the primary things that we see is of failure in the field, especially places that are exposed to higher climate or hotter climates, in particularly the southern part of the United States and other countries. The heat sinking is very important, not just inside the transceiver itself, but then into the receiver that the transceiver sits in. And that receiver then has heat dissipation into the housing to manage that temperature, because there's a lot going on in there.
Yeah, and then so there's actually a couple other things I wanted to add to that piece. So one is, as the environmental like conditions fluctuate and you're going from hot to cold, it also actually, this is more important for when we start talking about DWDM in particular, that temperature change will change the wavelength that is being transmitted. So another component that I didn't include in this, but is probably important, is the thermal microcontroller. So basically, the TOSA compensates for the environmental conditions so that you never see any sort of wavelength drift. And it's not as important for a wideband, 850 nanometer that can go anywhere from 830 to 870. But when you get into DWDM networks, and we're talking, an optical signal that needs to be to 100th of a nanometer accurate, or a 10th of a nanometer accurate, that's when it certainly becomes important to have that component.
For sure.
Secondly is the impact that temperature has on the lifespan of the optic as well. So, if you have a transceiver operating at room temperature, you'll get an MTBF of, it fluctuates depending on manufacturer, but for the sake of the discussion, it's about 250 years. However, if you change that operating temperature from 30 degrees Celsius to, say, 55 or 70 or even 85, you accelerate the aging of that optic to where that 250 years now becomes 25 years for a mean time between failure. And so to expand upon that, 25 years basically means if you have 25 units out in the field, you're going to have a failure within a year.
Yeah, well, first of all, thank you for defining MBTF and beating me to that. Or another initialism that we snuck in there, but you did define it. So yeah, the mean time to failure before failure is important. But just to reemphasize for our audience that heat sinking, particularly in the higher throughput optics, is extremely important, which means making sure that your SFP is properly seated in the receiver. Make sure that your receiver is properly tightened to the backplane, whatever that is, whether it's a housing in a node or you have plenty of rack space and cooling in the head end, so that these things don't overheat and shorten their lifespan.
Yeah, that actually also reminded me too. When you plug in SFPs, you don't need a hammer to plug them in. You definitely need to, you should be able to push it in with your thumb and be fine. I know you're laughing, Mike. I've had troubleshooting calls where guys like, yeah, I tried plugging in. I mean, like, how hard do you have to push it? I tried hitting it with a hammer, and I'm like, oh God, I really hope you didn't do that.
All else fails, use a bigger hammer.
Right.
All right. So now we know what's in the box in the transceiver. What's next?
So this slide I like to use as a way to kind of make sure we're all on the same page when we start talking about like kind of a higher level of what the network looks like. So host 1, transceiver 1, you've got transceiver 2 on the far end. The physical path is, and right here I've got a fiber from one host to the next, but out in the field you've got patch panels, muxes, basically everywhere the optical signal passes through, we call the physical path. And then lastly, like number 5 here is the far side of the link. So you've got your second host, your transceiver on the far end as well.
So in practical application, the physical path could be 2 fibers or it could be 1 fiber. But the important part is, the connection at the host to the transceiver.
Yes. This one kind of gives you a little bit of the scale of SFPs versus QSFPs versus QSFP-DDs. Don't think there's a whole lot more to say on this. I think for those that have never worked with SFPs, I mean, an SFP is maybe this, half the size of, probably about the size of my pinky. Maybe some other people have bigger pinkies than I do. I don't know. They're small. Some people call them thumbsticks.
Oh yeah, they are about the size in some cases of like a USB memory stick or a thumb drive or something like that. I just happen to have one here, a memory stick that's approximately the same size as an SFP.
Yeah, pretty much.
So they are pretty small, which is why they're called small form pluggable optics.
Yeah. And then here, we did talk about the components of the SFP. Here kind of shows as you get into some of the higher data rates, there are some changes. So like the CDR and an SFP and a QSFP get swapped out with a digital signal processor when you get to the 200 gig and 400 gig and above data rates. But by and large, pretty much the same sort of components otherwise.
So the one thing that we've kind of glossed over is sort of the definition of terms, right? You have the host side or the electrical side, and that's the part that plugs into the host or the backplane, and then the media side is the optical side where you plug in your optics. So just to baseline on our description of terms, or the host side versus the media side, or the electrical side versus the optical side.
Oh, yeah. Thank you. That was good. Yeah.
I hope you find today's video on SFPs informative and entertaining. And don't forget to stop back next week for the next part in this series of training videos.